Hello everyone, welcome to the BioTuber. I am Swastik and today we are going to look into the properties of amino acids. In last class, we talked about the basics or introduction to the amino acids along with biomolecules and in general protein and amino acids. Today we are going into some of the depths of the proteins or amino acids by looking into their properties. And we are going to start with the optical properties. So what are optical properties? Basically, optical properties are shown by the compounds which are optically active or which have a chiral center or chiral compound. Now, in case of amino acids, since we can see from the structure of the general structure of the amino acid that the central carbon is surrounded by four different groups, that is a amino group, a carboxyl group, a H atom and a R group. So since all these four groups are different, the central carbon is a chiral carbon that is surrounded by four different groups. In general, these four groups can be four different functional groups. For in this case, there are two or three different groups and a hydrogen atom. So all the amino acids are optically active, or we can say chiral in nature, except for glycine, because in case of glycine, the R group is simply another H atom, which makes it a chiral in nature. Now, so as I already mentioned that all the chiral compounds are optically active. That is, they can rotate the plane of a polarized light. That is, if a plane polarized light is passed through a optically active or a chiral compound, then the sample or the compound can rotate the plane of the polarized light in either of the one direction, that is either in clockwise direction or in anti-clockwise direction. That is, we can consider clockwise to be right and anti-clockwise to be left direction. Now, it is a simple illustration is drawn, that is when an unpolarized light source is passed through a polarizer, the unpolarized light is converted into plane polarized light. And then when this plane polarized light is passed through a sample or a tube containing the optically active sample, then we can see a rotation of the plane. So what is an unpolarized light and what is a polarized light? Light, as we all know, is a transverse wave. That is, it has the direction of propagation of light is accompanied by an electric field and a vibrating magnetic field as well. So since there is vibration of particles along the different planes, the light that we usually see, that is the sunlight, the bulb light or whatever source of light we are using, these are in general unpolarized in nature. That is, the vibration of the particle can happen in any plane. But when they are passed through a polarizer, which basically traps the different directional vibration and allow only vibration of the particle in one plane to pass through the polarizer, so we get a plane polarized light. And when this is passed through the sample, we can see the observed rotation. So under this condition, two cases can happen. The first one, that is the rotation is in clockwise direction. So if the observed rotation is clockwise, that is towards the right, it is considered as positive and denoted by small d, which is actually short form for dextrorotatory. Whereas for anti-clockwise, if the sample rotates the plane of the polarized light in anti-clockwise direction, it is negative, that is minus, or considered as levorotatory. Now, so how this is measured actually? So this is this optical activity of any chiral compound, or in this case the amino acids, is measured using a polarimeter, which is an instrument specific for this purpose. Now, how will the polarimeter measure? In what terms? So the magnitude of measurement for the optical activity is in angle of rotation, which is in degrees, and it is a quantitatively measured actually using optical rotation alpha. It is denoted by alpha. Now, since the wavelength are different kind of wavelengths can be used, temperature may vary, the concentration of compound can vary, alpha depends on a number of factors. That is, it can depend on the concentration of the compound, the temperature, the path length of exposure to that particular wavelength of light, and the wavelength as well. So what we observe is the observed rotation, and that is actually converted into specific rotation. And this conversion is made using this formula, where alpha from T to lambda, that is at a particular temperature and a particular wavelength, is dependent or is equal to A naught, that is the observed rotation, divided by the product of path length and the concentration of the sample or the chiral compound. So as mentioned, this alpha is the specific rotation which is measured in degrees. Alpha is the specific rotation and A naught is the observed rotation which is in degrees. L is the path length and C is the concentration of the compound which is measured in gram per ml. The path length is actually measured in decimeter quantity, so always remember to convert the given dimension into decimeter and this gram per ml, because questions can come about the concentration given in micromolar range or different concentration terms. So we have to convert this into specific notations or specific measurement units, and then the calculation to be done. And these kind of questions can come in CSIR as well as different entrance exams. Now, apart from this, now we are going to look into the absolute configuration of amino acids. Okay, so let's start with the absolute configuration of amino acids. Amino acids can exist in two different configurations, which are non-superimposable mirror images to each other. For instance, let's take the example of this hand. So if it is one of the chiral compound or one of the amino acid, so it is one of the form and this is another form. So these two are actually mirror images of each other, but they are non-superimposable. That is, if I try to superimpose these two, then they are not the exact match and they are simply the mirror images of each other. The similar happens with case of amino acids as well. In case of amino acids, there are two different configurations and it is possible because of again the presence of a chiral center. Now, in case of amino acid, the DL system is followed on the basis of the DL system of glyceraldehyde. So it is actually depending on what are the D and L form of glyceraldehyde, the D and L form of amino acids are also measured or detected. So let's take the example or see how actually glyceraldehyde is present. In case of glyceraldehyde also, we can see there is a central carbon atom which is surrounded by 4 different groups, making it a chiral center. And in this case, the 4 different groups are a CHO, that is the aldehyde group, a alcoholic group, a hydrogen atom, and a methyl alcohol, we can say, that is CH2OH. So when the OH group is present on the left hand side of this structure or this arrangement, it is called as the L-glyceraldehyde. Whereas when the OH group is on the right hand side in this arrangement, it is called as the D-glyceraldehyde. And this similar notation is followed for the amino acids as well. For example, let's see, this is the general structure of amino acids as we have studied. So in this case, there are 4 different groups and these 4 different groups are present or arranged around the central carbon atom in different directions. Now, if the amino group is present on the left, which is like similar to the L form of glyceraldehyde, it is termed as the L-amino acid, whereas when the amino group is present on the right, similar to that of the glyceraldehyde, it is present called as the D-amino acid. Now, this is followed by all the amino acids which are chiral in nature. So again, the exception is there, that is glycine. Since glycine, the R group is a H atom, it does not follow the same principle. Another important thing that is to be noted is that all the proteins that are naturally occurring or ribosomally synthesized or naturally found are L-amino acids. That is this L form is seen where the amino group is on the left hand side. And in general, as we know that all amino acids are alpha amino acids that we have studied earlier because of the priority of amino group, where amino group and carboxyl group are both bound to the alpha carbon. These are overall called as the L-alpha amino acids, which are naturally found. There are some D amino acids also are seen in case of antimicrobial peptides, but they are not common and are quite rare in nature. Another configuration that is followed is the RS system. Okay, so let's see the RS configuration. So in case of RS configuration, the R stands for rectus, that is the Latin for right, and the S stands for sinister, that is the Latin for left. In the RS configuration, the groups around carbon atom, that is the chiral center, is prioritized on the basis of decreasing atomic number. That is, the groups which are attached to the central carbon are prioritized on the value of their atomic number. That is, the higher atomic number value are given the highest priority and the lowest atomic number value are given the least priority. So let us take a look at an example and know how it is done. So for this example, I have taken the case of alanine, where the 4 different groups are amino group, a methyl group, a hydrogen atom, and a carboxyl group that we know. Now, since the 4 groups are different, among these 4 groups, nitrogen has the highest atomic number, that is 7. And after nitrogen, there is carbon. So nitrogen is given the first priority, and then there are 2 carbons. So again, now the question arises, which carbon to be given the second priority? So the carbon, if the 2 second priority elements are the same, then we have to look for the next element in the same group. So in case of this carboxyl group, the second element is the oxygen atom, whereas in case of the methyl, the second element is a hydrogen atom. And we know that oxygen has a higher atomic number, that is atomic number of 8. It is given the second priority over hydrogen. So the carboxyl group is given the second priority, followed by the methyl group, and hydrogen, since it is the first atom in the periodic table, it is given the last priority. On this basis, if we go on prioritizing, this gives a clockwise rotation. That is, a clockwise rotation can be seen. And in the second case, if we see, the amino group has no doubt the first priority because nitrogen is there, which is followed by again carboxyl group and methyl group, and it follows a different pattern, that is the anti-clockwise pattern. So on this basis, actually, how the priority series are found around the carbon atom, that is in clockwise or anti-clockwise direction, the RS system or RS configuration is determined. That is, in clockwise, that is right, that is the rectus form, and in anti-clockwise, that is the left, it is the sinister form. So again, there is like all the amino acids that are biologically synthesized exist in the S form, that is the sinister form, except for cysteine. So that will be all for today. If you like this video, do subscribe to my channel, and we will be having newer topics in the coming sessions. Thank you.